All right, unfortunately, a few days ago, my permission to use the project name in this talk was revoked, and I was instructed to remove references to it and any location names in the following presentation. So I apologize if I'm overly obtuse by continually referring to this motorway or this interchange or in this example, but apart from making me sound like a bit of a wally and probably other words starting with W, it should not really make much difference to the whole point of this talk, which is just to share design ideas. So some may be new ideas and techniques, but some will just be old and probably just forgotten at times. Motorway upgrade or even just simply road design techniques are common between similar projects. So some of the examples and techniques we would probably have relevance to a lot of the work that we all do in 12D. And the only reason for normally presenting these ideas under the banner of a real-life project is to give it real-life context rather than show solutions specific or unique to a particular area. Our current motorway upgrade project is a typical large concept level design, upgrading 60 kilometres of dual carriageway. The project involved around a year's work, starting in early 2015, and was our first 12D synergy project, and in fact probably the first actual commercial 12D model project to be run in 12D synergy anywhere. The project was also our first to make heavy use of several design snippets I wrote before and during the project. And this talk is an opportunity to share some of the ideas we came up during the course of the actual project, both relating to the design and how we actually tackled it in 12D, plus hopefully also just pass on some technical insight that we may have gained through the experience. The typical focus of upgrade projects like this is primarily to address motorway capacity issues and usually involves adding extra lanes in each direction. This invariably means reconfiguring many of the interchanges to match these extra lanes, as well as resolve deficiencies in most of them. And this talk will show just a few of the challenges and some of our proposed solutions and that we actually applied during a typical project. And then I'll move on to the main focus of this talk, which is really to talk about superelevation application and flat topography. So one of the common motorway traffic issues to resolve with motorway upgrades relates to weaving problems with traffic from adjacent interchanges that now wind up being too close for the proposed number of total lanes now carried by the motorway. And in this example, the northbound traffic from major arterial road wanting to exit at the next interchange are in conflict with high traffic numbers heading north from the merging motorway trying to get out of the same lane, which is then trapped at the next exit. And the southbound on-ramp traffic wanting to head down the major arterial road are in conflict with dopey highway traffic, not realising they need to move over into the same outside lanes to continue down the motorway. And besides the safety aspects of something like this, the merge conflicts can be so severe that they actually impact on motorway capacity. So we modelled up several options in 12D to help us assess a best and practical solution. Having a system in 12D which allows you to rapidly move a design to an option then back to design again is a critical part to be able to quickly float ideas to the traffic modelling and estimation teams to assess the pros and cons of each option. And a simple copy and rename of a job should be all that is actually required to actually move between a base design and options. Interchange options we inevitably have to investigate generally escalate in complexity until sanity finally prevails and we dial it back a notch to a design that we feel has the right balance between function and practicality. In this example of a typical solution, the southbound on-ramp traffic connected to the major arterial road via grade-separated correction road that utilised the free span under the existing motorway overpass. And the northbound traffic is moved to the outside lane prior to the northbound motorway merge. Our design layout is then passed to the traffic nerds to model, and in this example, the resulting traffic flows are combined with a visualisation model that shows actual modelled traffic volumes and not the random traffic patterns that are typically shown in these kind of visualizations. So one of the admirable qualities of the 12D development team is that they're always on the prowl for ideas and new features, and of course no talk like this would be complete without a gratuitous enhancement request. So how about the ability to generate timeline vehicle traffic based on the Vism FZP export, which would turn timelines into an incredibly valuable design tool and allow us to quickly communicate our solutions in a format that non-modelers can understand, and it would also put you yet another leap ahead of your competition. A typical problem with interchange capacity relates to congestion caused by high ramp cross-traffic movements, and a preferred solution after yet another iterative round of design optioneering maybe a diverging diamond, a popular solution in the USA and Europe, but to date only used once in the Southern Hemisphere in my old stomping ground of KwaZulu-Natal in South Africa, where an award-winning design by AECOM was built back in 2013. And the concept behind these interchanges is the switch inside of traffic flows to favour the ramp turning movements, and capacity improvements of up to 60% have been claimed. The perceived downside relates to the dangers of drivers being confused about being forced onto the wrong side of the road. So removing any doubt through careful, unambiguous geometry and signage is an important part to a design like this. These types of interchanges are being considered by Main Roads in Queensland, Western Australia and Vic Roads in Melbourne, so it may only be a matter of time before Australia gets its own diverging diamond, also affectionately known as DDRs by the Interchange-Traffic. And if you think I'm exaggerating, be sure to visit www.divergingdiamond.com. In this example, apart from the reconfiguration of the current interchange, we also investigated the inclusion of a bypass under the interchange to accommodate a steadily increasing traffic stream from the service road north of the bridge, which will no doubt go completely mad with all the breeders and meatball junkies when this well-known department store will open its doors later on this year. The design of all the interchanges in the project gave us the opportunity to implement some new ideas in using design snippets to automate and streamline the design process. And by pre-populating these from a range of MTF seed files, which are chosen when creating the MTF of an on or off ramp, the laying out of a design can be incredibly quick. So as an example, once the alignments are prepared using a name position on the motorway alignment, the motorway component of the off ramp is applied with a snippet that generates the auxiliary lane, ramp, throat, and gore area. The MTF for the off ramp is generated from an MTF seed file that is pre-populated with the appropriate left and right templates, fixed interface snippet, and other options such as the ability to add a second lane after the nose, as well as trimming the edge strings to form the off-ramp gore. This may ultimately become a single ramp snippet with all these options built in as snippet choices. The development work never really ceases when you work in 12D. I am ever wary of making snippets too complicated to debug, especially after I win the lotto and somebody else has to do this. Another task in motorway upgrade project may be focused on finding practical solutions to address major flood event inundation, which can cut major transportation routes like our main highways, while simultaneously alleviating the excruciating Sunday afternoon crawl that any Brisbaneite dreads. Typically, existing bridges as a general rule cannot be widened to accommodate the extra lane, primarily due to their age, that and the fact that many of them appear to be built on chopsticks. Their safety barriers now also fall woefully short of current design standards for 120 kilometers an hour. But on the bright side, my rising panic of being trapped upside down, slowly sinking into the black waters of the swamp, would be somewhat mitigated by the distraction of having this 6-inch thick pole sticking out of my chest. So there is always a silver lining in life if you look hard enough. There are a few things more idiotic than seeing an arbitrary note on a drawing like existing bridge to be widened and raised, with no consideration of how this is to be achieved under crazy traffic numbers on major routes like our highways. So unless your temporary traffic solution involves the use of skyhooks, or my personal favourite, the innovative car trebuchet, to get traffic past the bridge construction zone, your proposed solution does not give a true reflection of the ultimate cost, environmental or property impacts. Our alignment options we typically investigate revolve around fully and partial offline alternatives and to allow construction of these bridges, which would take months to complete, to be either free or partially free from existing traffic constraints. The primary difference between the two end results is the perceived loss of existing infrastructure and the extent of environmental and property impacts. Interestingly enough, our preliminary cost estimations on these alternatives show the fully offline to still be cheaper due to the vast costs and delays associated with dealing with all the highway traffic during construction. One of the other challenges we typically face are the generally flat longitudinal grades on many of the Queensland motorway projects I've been involved in over the years. And developing and applying superelevation safely requires a bit of understanding of identifying potential problem areas early in the design process so that you can plan accordingly. And this is where 12D is so good with work like this, because back with version 8 in 2010, we got design table-based superelevation, and we were quick to see the value in a utility like this. The critical part of this tool is the automatic presence of the superelevation diagram on the section view, where it can be viewed in conjunction with the longitudinal grading of the roadway. the location of the vertical alignment relative to the proposed crossfall transition areas is dynamically updated as the alignment is adjusted. And if you know what to look for, this is a huge time saver in reducing the amount of trial by error iterations to get a safe and practical solution. So while the aquaplaning risk assessment process is generally pretty well understood, the actual minimum slope of the road surface, which directly contributes to the estimated depth of flows, is often overlooked. Before even starting to draw flow paths and running Owen's excellent aquaplaning risk assessment tool, it is important to assess the resultant surface grades. So a simple slope range file combined with a TIN prompt and a parameterized chain allows for repeated rapid spot checks, which should confirm the alarm bell should already be ringing when the view's design contours and flow arrows lose their way through the crossfall transition zone. The dynamic nature of these contours and flow arrows are another excellent 12D tool, which gives us constant feedback on the state of our designs. Road surfaces within the road traffic lane should never be allowed to drop below an absolute minimum of 0.3% and probably a realistic desirable of around 0.5%, because this prevents adequate pavement layer through this area, weakening the pavement, which leads to rutting, more settlement, and you wind up designing a skid pan instead of a road, because surface flows entering this area never get to leave. The obvious locations for identifying and avoiding these flat spots are areas of zero longitudinal grade, such as crests and sags, where attempting to rotate your superelevation is never going to work and probably indicates you're not considering horizontal and vertical alignment coordination in your design anyhow. There is a more insidious situation that is difficult to identify without your superelevation diagram, and that is where a drop or rise in pavement edge levels generated through the superelevation rotation is countered by grade running in the opposite direction. The superelevation diagram is effectively a chart of the road edge levels relative to the reference string, and you can see that by dropping the pavement edge in super when on a downgrade effectively accelerates the change in levels through the zero crossfall point. Applying the same rotation on an upgrade slows down the effective rate at which these levels drop, and the result gets worse as the upgrade gets flatter, to the point that the road edge levels wind up pretty much flat. A much steeper upgrade reverses the direction of this level change, even though the crossfall is still dropping, but this still maintains a longitudinal grade through the zero crossfall point. So the simplest tactic is always to ensure that the road grade runs in the same direction as the crossfall change. A grade of 0.3% will always ensure that the resultant pavement slope never gets flatter than the absolute minimum. And the alternative is to provide a much greater upgrade, usually around about 2.5% for a three-lane lane rotation, to ensure the resultant surface grades stay above minimum. One of the important design decisions that need to be made early in the design process is where to place the axis of rotation or your control line in your cross-section. And as I've mentioned before, the simplest solution is to grade your superalignment to match the direction of the change in crossfall, but there are always two sides to any roadway. This means that your simple solution works on one side but not on the other. This means if your control line is placed inside the road lanes, you're always going to need a longitudinal grade of between 2 and 3% through your superelevation transition areas. And in flat topography, this usually isn't practical, particularly in brownfield or overlay projects like highway upgrades, where these induced grades result in vast areas of thick overlay, which are near impossible to construct and uneconomical. With the control line on the inside edge of the traffic lanes, the advert crossfall rotation causing low surface grades happens outside of the trafficked areas, where the width of road pavement is, rotated pavement is relatively small. This does mean rotating more lanes, which theoretically results in slower rates of rotation if the relative grade criteria is taken into account. But this is an appearance criteria only, and in the contest of safety versus pretty, safety is going to win every time. If the flow paths generated on this larger width of rotated pavement are an issue, there is always the option of a staged pavement rotation, where the application of superelevation is delayed or advanced on portions of this road surface. This splits the flow paths and reduces the depths of flows dramatically. A combination of design tables and named parts makes this a reasonably simple process to apply, where the automatic application of super is still applied to the outer lanes, while the inside lane is rotated with crossfall modifiers, then suppressed with more modifiers for the remainder of the automatic development. And using named parts in 12D means chainage-free reference points dynamically linked to the curved tangent point, so this will automatically adjust with further horizontal edits. The general rule is when raising the road edge, the inside part is rotated first, and when dropping the road edge, the outside parts are rotated first. It is also worth remembering that in off-roads, the rate of pavement rotation can be increased to 3% per second when aquaplaning is a potential issue, which also assists with further reducing flow path length and depth. An interesting solution that I've seen is discussed by Roy Spillane in a paper presented at a TMR seminar back in 2003. Something which would fall into the if all else fails category is the concept of a crown or crease running diagonally across the road pavement. Vehicles traversing over this crown experience a rotation equivalent to a conventional change in superelevation, and in theory, this treatment would allow superelevation to be applied at a 0% longitudinal grade. The standard rotation of cross-fall change per second experienced by the vehicle crossing the crown can be extrapolated to calculate the length of hinge per lane, which works at around 140 meters for a 6% change in crossfall at 110 kilometers an hour. The hinge is positioned so full super lane elevation is achieved at the curved tangent point, and we have found this easiest to create with a computated super alignment forming the crown, then generate a separate crossfall surface tin and draping the roadway strings with 2 tin modifiers. This diagonal crown technique has already been constructed by Downer on the Bruce Highway at Caboolture, but does come with constructability and maintenance issues, and you would certainly need to discuss this with your client and weigh it up against conventional alternatives, which may involve raising existing motorway levels up by more than a metre to get a safe grading solution. Working on this project offered us a series of interesting and challenging problems to solve, and we look forward to our time on the next stage of design where we can take these ideas one more step closer to reality. Thank you.